Hello everyone, this is Sirisha. In this video, I am going to discuss about the lattice structure of FIR filter. Let's see what a filter is. It is a device that uses to remove unwanted features in a signal. And what a FIR filter is? It is a filter with finite impulse response. It means the response of a filter is finite when impulse signal is given as input. For nth order FIR filter, the impulse response becomes 0 after n plus 1 samples. When the linear phase is important for a filter, we go for FIR filters. Let's see the structure of FIR filter. FIR filter can be represented in 4 different structures and one of them is lattice structure. Here H of Z is the system response and Hm of Z equal to Am of Z represents the sequence of system functions, where Am of Z is given by the equation 1 plus sigma k equal to 1 to m alpha m of k into Z power minus k. Here m is the order of the filter and k is ranging from 1 to m. And alpha m of k here represents the unit sample response of mth filter. And y of z is the response of output signal, which is given by response of the system into response of the input signal. By substituting the sequence of system functions in the above equation, we can get y of z as x of z into 1 plus sigma k equal to 1 to m alpha m of k into z power minus k. By applying inverse Z transform for the equation, we can get y of n as x of n plus sigma k equal to 1 to m alpha m of k into x of n minus k. Let's find out the output of a first order filter using this equation and also using single stage lattice structure. First of all, let's compute y of n using this equation. For a first order filter, m is 1. So substituting m equal to 1 in this equation, y of n equal to x of n plus alpha 1 of 1 into x of n minus 1. Let's compute the output using the single stage lattice structure. This is the lattice structure of a first order FIR filter, where x of n is the input signal. Here f naught of n and g naught of n are same as x of n, where g naught of n is passed through a delay element z power minus 1, so it becomes g naught of n minus 1. For the first adder here, f naught of n is given directly and g naught of n minus 1 is given through a reflection coefficient k1. And for the second adder, f naught of n is given through a reflection coefficient k1 and g naught of n minus 1 is given directly. So the output of this system is y of n, which is given by f naught of n plus k1 into g naught of n minus 1. And g1 of n is given by k1 into f naught of n plus g naught of n minus 1. By replacing f naught of n and g naught of n with x of n in these equations, we can get output of the signal as f1 of n equal to x of n plus k1 into x of n minus 1. It is same as the one we computed before, where k1 is nothing but alpha 1 of 1. Similarly, let's compute the output of the second order filter. This is the lattice structure of the second order filter. Here the first stage of this filter is similar to the single stage lattice filter. Here f1 of n and g1 of n are the inputs for the second stage of second order lattice filter. We already computed f1 of n and g1 of n. Here g1 of n is given through a delay element z power minus 1, so it becomes g1 of n minus 1. The first adder is given with f1 of n and reflection coefficient k2 times g1 of n minus 1. So the output of this filter is f1 of n plus k2 times of g1 of n minus 1. By substituting the computed values of f1 of n and g1 of n, we can get the output as x of n plus k1 into 1 plus k2 times x of n minus 1 plus k2 times x of n minus 2. The output of the second order filter using the equation y of n equal to x of n plus sigma k equal to 1 to m alpha m of k into x of n minus k, we can get the output as x of n plus alpha 2 of 1 into x of n minus 1 plus alpha 2 of 2 times x of n minus 2. By comparing these two equations, we can observe that alpha 1 of 1 equal to k1 times of 1 plus k2 and alpha 2 of 2 equal to k2. By observing the outputs of the first order filter and the second order filter, we can compute the output of the nth order filter using the equation fm of n equal to fm minus 1 of n plus km into gm of n minus 1, where fm of n is the output of the nth order filter f m minus 1 of n is the output of the m minus 1th order filter, where km is the reflection coefficient of mth stage of a filter. And gm of n is given by km into fm minus 1 of n plus gm minus 1 of n minus 1. This is the structure of mth order lattice filter. Here capital M is the length of the filter. For a m length filter, it consists of m minus 1 stages, where m minus 1 is the order of the filter. Here K1, K2, K3 and so on, Km are the reflection coefficients of mth order filter. The output of the mth order filter is given by sigma k equal to 0 to m, alpha m of k into x of n minus k. And gm of n equal to sigma k equal to 0 to m, beta m of k into x of n minus k, where beta m of k is given by alpha m of m minus k. We can realize the lattice structure of a FIR filter, mth order FIR filter, if its system response is given. Here am of z is the system function with coefficients alpha m of k, and bm of z is the system function with coefficients beta m of k, where beta m of k is alpha m of m minus k. We can get bm of z as z power minus m times of m of z inverse by solving this equation. If we want to find out the system function for m minus 1th order filter, am minus 1 of z is given by am of z minus km times of bm of z by 1 minus km square, where km is the reflection coefficient of mth stage. If am of z is 1 plus a1 times of z power minus 1 plus a2 times of z power minus 2 and so on am times of z power minus m, here the leading coefficient am is nothing but the reflection coefficient of the mth stage. Similarly, we can find the reflection coefficient of m minus 1 stage from am minus 1 and reflection coefficient of m minus 2 stage from am minus 2 and so on. After finding all these reflection coefficients, we can realize the lattice structure by using adders, delay elements and these reflection coefficients. This is the mth order lattice structure of a FIR filter, where y of n, which is nothing but fm of n, is the output of this filter. Let us see an example where the system response is given and asked to realize the lattice structure. To realize the lattice structure, first of all we need to compute all the reflection coefficients. By comparing am of z with h of z, we have the leading coefficient a3 as 1 by 4. So the third stage reflection coefficient k3 is 1 by 4. To compute k2, we need to find out a2 of z, which is given by a3 of z minus k3 into b3 of z by 1 minus k3 squared, where b3 of z is z power minus 3 times of a3 of z inverse. By solving this, we can get b3 of z. By substituting a3 of z, k3, b3 of z in this equation, we can get a2 of z as 1 plus 2 by 3 times of z power minus 1 plus 1 by 3 times of z power minus 2. So here the leading coefficient is 1 by 3. So the second stage reflection coefficient is 1 by 3. Similarly, to find k1, we need to find out a1 of z. Beta of z equal to z power minus 2 times of a2 of z power minus 1. By solving this, we can get beta of z. Substituting beta of z, a2 of z and k2 in this equation, we found a1 of z is 1 plus 1 by 2 times of z power minus 1. Here the leading coefficient is 1 by 2. So the first stage reflection coefficient is given by 1 by 2. Now we have reflection coefficient for each stage. Using these reflection coefficients and adders and delay elements, we can realize the lattice structure in this way. Here f1 of n is the output of the first stage, which is given by x of n plus k1 times of x of n minus 1. And f2 of n is the output of the second stage, which can be given by f1 of n plus k2 times of g1 of n minus 1. By substituting f1 of n and g1 of n minus 1, we can get f2 of n as x of n plus 2 by 3 times of x of n minus 1 plus 1 by 3 times of x of n minus 2. And the output of this lattice structure is y of n, which is equal to f2 of n plus k3 times of g2 of n minus 1. By substituting f2 of n and g2 of n, we can get y of n as x of n plus 3 by 4 times of x of n minus 1 plus 1 by 2 times of x of n minus 2 plus 1 by 4 times of x of n minus 3. Thank you.